Welcome to The Explainer. Today, we're getting into a core idea in chemistry, one that explains everything from a simple campfire to the complex machinery inside our own bodies. We are talking about activation energy. So, have you ever really thought about this? You've got a match, you've got the box. They can sit next to each other all day long and nothing happens. But the second you strike them together, poof, you get a flame. That isn't magic. It means there's some kind of invisible energy barrier that has to be crossed first. And today, we're going to figure out exactly what that barrier is and, more importantly, how to get around it.
All right, here's our game plan. We'll kick things off with the absolute basics of any reaction. Then we're going to picture this whole energy barrier thing as a huge mountain we have to climb. After that, we'll look at the clever shortcuts chemists use to make the climb easier, meet the different guides for this journey, and finally, we'll see why this whole chemical climb matters so much in our day-to-day lives.
Okay, first things first. You can think of every single chemical reaction as a journey. And like any good journey, it's got a beginning and an end. Let's get our terms straight. So you always start with your reactants. These are just your starting ingredients, the raw materials you're working with, and you end up with your products, the new stuff that gets made. The entire goal of a chemical reaction is to turn those reactants into products. But here's the catch. It's almost never a simple straight line from A to B. And that right there brings us to the heart of it all. See, standing between your starting point and your destination, there's usually this massive hill, an energy mountain that everything has to get over first. And that climb, that's what chemists call activation energy. It's the absolute minimum energy kickstart you need to get the reaction going. It's like the entry fee you have to pay for the reaction to even be allowed to start. No energy in, no reaction. Simple as that. Now, right at the very peak of that energy mountain, you hit this super unstable, high energy point called the transition state. It's this fleeting moment where the old chemical bonds are breaking and the new ones are just starting to form. This is the tipping point, the point of no return. So how do you figure out how big this climb is? Well, it's actually pretty straightforward. The activation energy is just the energy at the very peak, that transition state, minus the energy you started with. It's literally just the height of the mountain from where you began. And here is the single most important takeaway. The size of that mountain changes everything. A really, really big mountain, a high activation energy, means the reaction is going to be incredibly slow because only a few molecules will have enough oomph to make it over. But a small hill, well, that's easy to get over, and the reaction happens way, way faster. A huge energy mountain can be a serious roadblock, right? But what if you didn't have to climb over it at all? What if there was a shortcut? Well, that's where catalysts come into play. Okay, so let's picture that big energy mountain again. Without any help, our reactants are staring up at this tall, steep barrier. It's a tough climb. It's going to take a while. But now, watch what happens when we add a catalyst. Look at that. The catalyst doesn't give the reactants a push up the old mountain. Oh no, it does something way smarter. It creates a brand new path altogether, a much, much lower one. It's like it built a tunnel through the mountain. The destination is exactly the same, but the journey just got a whole lot easier. You can think of catalysts as little chemical matchmakers. They grab the reactants, they hold them in just the right position, and they make it way easier for them to react. They lower that energy barrier and speed things up, sometimes by millions of times. But, and this is the magic part, once the reaction is done, the catalyst just lets go, completely unchanged, ready to do it all over again. So, it turns out catalyst isn't a one-size-fits-all job description. There are different kinds of these chemical trail guides, each one with a very specific purpose for the journey. We can basically break them down into three main groups. You've got your positive catalysts, which are like hitting the accelerator. You've got negative catalysts, which are more like slamming on the brakes. And then there's the really wild one, the auto catalyst, which is kind of its own self-starter. So the positive catalyst is the one we think of most often. Its whole job is to speed things up. A classic example is making ammonia for fertilizer. That reaction is naturally painfully slow, but you throw in some simple iron as a catalyst, and suddenly it's efficient enough to help feed billions of people. It's a huge deal. But what's really interesting is that sometimes you actually want to slow a reaction down. And for that, you need a negative catalyst, or an inhibitor. They basically do the opposite. They make the energy mountain higher or block the easy path. This is super useful for things like keeping food from spoiling or stopping medicines from breaking down too quickly. And now for my favorite, the autocatalyst. This is where things get really cool. It's a reaction where one of the products you make is also the catalyst for the reaction. So it starts off slow, but as it makes a little bit of that product then speeds up the reaction, which makes more of the product, which speeds it up even more. It's this incredible self-accelerating chemical feedback loop. So we've got this energy mountain, we've got these shortcuts, but what does any of this mean outside of a chemistry lab? Well, the answer is just about everything. So let's just quickly recap what we've learned. Every single reaction needs that little energy push to get going. That's the activation energy. The bigger that push, the slower the reaction. But we can use catalysts to build shortcuts, lowering that energy barrier to make things happen faster. And having this control isn't just a neat trick, it's absolutely essential for industry, for biology, for modern life as we know it. You know, the enzymes in your body right now are just tiny biological catalysts running all the reactions that keep you alive. The catalytic converter in your car is using catalysts to clean up your exhaust. So I'll leave you with this question. As we get better and better at finding and designing these chemical shortcuts, at truly mastering these energy mountains, what other massive problems could we solve? What new worlds could we build?